Background: Auger cascades generated in high atomic number nanoparticles, NPs, following an ionization were considered as a potential mechanism for the NP radiosensitization. The Auger electrons have short ranges and can locally damage tumor cells, resulting in larger biological effect than radiation alone. In this work, we investigated the microdosimetric consequences of the Auger cascade using the theory of dual radiation action (TDRA) and proposed a novel bomb model as a general framework for describing NP-related radiosensitization. When triggered by an ionization event, the bomb model considers the NPs that are close to a radiation-sensitive cellular target generate dense secondary electrons and kill the cell according to a probability distribution, acting like a bomb. Methods: TDRA plus a distance model was used as a theoretical basis for calculating the change in alpha of the linear quadratic survival model and the relative biological effectiveness, RBE. In TDRA, cellular lesions are assumed to be formed as a result of the combination of pairs of sublesions, example, chromosome break, in the sensitive sites of the cell. In addition, the yield of sublesions formed within spherical sites is assumed to be proportional to the energy deposited to the site. We calculated the quantities for SQ20B and HeLa human cancer cells under 250 kVp X-ray irradiation with the presence of gadolinium-based NPs, AGuIX, and to 20 kVp X-ray irradiation with the presence of 50 nanometers gold NPs, ONS, respectively, and compared with existing experimental data. Ghent-4-based Monte Carlo, MC, simulations were used to 1. Generate the electron spectrum and the phase space data of photons entering the NPs and 2. Calculate the proximity functions and other related parameters for the TDRA and the bomb model. Results: the Auger cascade electrons have greater proximity function than photoelectric and Compton electrons in water by up to 30%. But the resulting increases in alpha are smaller than those derived from experimental data. The calculated RBEs cannot explain the experimental findings. The relative increase in alpha predicted by TDRA is lower than the experimental result by a factor of at least 45 for SQ20B cells with AGuIX under 250 kVp X-ray irradiation, and at least 4 for HeLa cells with ONS under 220 kVp X-ray irradiation. The application of the bomb model to HeLa cells with ONS under 220 kVp X-ray irradiation indicated that a single ionization event in NPs caused by higher energy photons has a greater probability of killing a cell. NPs that are closer to the cell nucleus are more effective for radiosensitization. The comparison of HeLa cell with ONS irradiated with photons of different energy implies that NP ionization by photon of higher energies have higher killing power, and the Compton scattering in NP may have a stronger effect than photoelectric effect, even though the latter can result in Auger cascade. Conclusion: microdosimetric calculations of the RBE for cell death of the Auger electron cascade cannot explain the experimentally observed radiosensitization by AGuIX or AGuIX. while the proposed bomb model can be a potential candidate for describing NP-related radiosensitization at low NP concentrations. Conclusion: microdosimetric calculations of the RBE for cell death of the Auger electron cascade cannot explain the experimentally observed radiosensitization by AGuIX or AGuINP.